Our next speaker, Dr. Jason Mann, as the R&D manager of MCi Carbon. So Dr. Mann holds a PhD in chemical engineering from the University of Sydney. His postdoctoral research focused on the fundamentals of high-temperature mineral phase transformations and the kinetics of gas, liquid, solid mineral dissolution reactions, and the application of this knowledge to CO2 mineralization process development. He leads MCi's R&D program, where the company is focused on translating the outcomes of 10 years of mineral carbonation research into a commercially viable industrial process for CO2 capture and conversion. He leads a team of process engineers, chemists, and material scientists in developing MCi's products for applications in construction and industry, and scaling up the process towards commercial deployment. Please join me in welcoming Dr. Mann.
It's always really weird having people talk about you like that. So, well, before I start, I want to say David and Kane and Mitchell, great presentation so far, and I think it's good. A little bit about MCi Carbon and how we fit into this picture. Kane highlighted it perfect just then. You have, when you're looking at clinker production, you have a big whopping 500 kilograms of CO2 per ton of clinker associated with the geogenic emissions. And MCi's business model has been around creating solutions for decarbonating these hard-to-abate industries. So clinker is a good example, but anything that pretty much calcines a carbonate. So you have refractories, magnesium carbonate, and you have lime, and lime's just everywhere, like you can think anywhere. We've taken on that strategy and we've looked at, number one, reducing the emissions from it, but that doesn't really solve much because you've just created another solution. You now need to deal with that CO2. So what we do is we engineer it into a material that can feed back into construction industries that typically use CO2 intensive materials. And one way of that is SCMs, and other way of that is limestone products and carbonate products. MCi is a company, it started around 2014, has about 40 employees today. And it originally started as a joint venture between a Canberra startup, New South Wales State Government, and the University of Newcastle, and Orica as an industrial partner. We did some work with Boral. That's when Ross Harper was back in his general manager EGM days. And we developed the technology, they like to say, in secrecy over that last decade or so. What the technology is in a nutshell, if we walk through what we do, is that we start with a feedstock, and that has to be an alkaline feedstock, and that can be natural silicate materials, that magnesium or calcium silicates. I'm going to get a bit sciencey here, so bear with me. It can be waste materials such as slag. So when I talk about slags, I'm talking about electric arc furnace, BOS slags, from either integrated steelworks or the more kind of evolving electric arc furnace for direct reduction type materials. That material is crushed down, it's pre-treated, so it increases its reactivity towards CO2. We then slurry it up in a process, and then it's contacted with CO2. And what makes our technology different to the consortium of pathways out there is that we've been able to take direct from flue. So what does that mean? You can take CO2 direct from your clinker kiln and pass it directly through our process without having to concentrate up that CO2. During that process, everyone knows what a soda stream is. The CO2 dissolves in the water. You have a reaction where the CO2 or the carbonic acid reacts with the magnesium and calcium, and you can create your calcium or magnesium carbonate products. Depending on what the feedstock is, if it's a slag, you end up with a conditioned slag. So if anyone knows anything about slag treatment and slag utilization industry, it needs to go through a conditioning stage. Our technology helps to accelerate that. In the case of natural feedstocks or silicates, you produce an amorphous silicate material. So essentially you remove the alkaline components from that, so the magnesium or the calcium, and you create a reactive silicate. What my kind of work at MCi does, and what my team does, is we look at how to utilize those technologies. So MCi has a large engineering team that looks at the upfront processing components of it. So what does the technology look like? What do we have to do to get the reactions that we want? But my role at MCi is how do we make these materials and how do we get them into industry and get them to work. So as part of that, and in the method today, MCi has quite a significant project in Smartcrete CRC, and we're looking at developing up our materials as SCMs, but then we've also got a number of connections through industry partners where we're looking at utilizing our sand and our slag-based products and our silicates in concrete, so that a lot of these companies have been already mentioned today indirectly, and they're the type of people that we're working with to get those materials out. Kane, you made a statement saying that no one's doing it. That's true. No one is doing it at scale, but we've got a pathway or a roadmap in terms of how we're going to roll the technology out. Today, we've got a global reference pilot plant. So this is where I work at Newcastle University. The reason it's at the university originally stems from that joint venture that was originally put together with them as a key component. Today, we're very different. The MCi is actually a combination or a joint venture between a number of corporations. Atoshu Corporation is one of them, who's a big supplier of blast furnace slag into Australia. But we also have RHIM, who's a leading refractory producer in Austria. And they're one of our first kind of commercial partners in terms of developing this technology to scale. So at the moment, what you see here is a large amount of equipment. But what we have is essentially everything in that wheel goes on in this plant here. We process about 10 tons of CO2 per year at this scale, not run continuously. It's a research pilot plant. So what we do here is we look at all different feedstocks. So when I say what type of feedstocks, we can take waste. So one project that we have coming up is actually looking at waste concrete or classified waste concrete, where they've recovered the cured cement component or the slurry from it. But we also look at different projects looking at different types of slags, so converter slag, electric arc furnace slag, ladle slags, where we're processing through our technology, looking at how they react with CO2, but then also what do those products look like. In terms of our scale up, so we talk about the pilot plant, which is now, we're currently towards the actual final stages of the construction of our, what we're calling Myrtle, our demonstration scale. So this is treating about 1,000 tons of CO2, 1,000 kilograms, so I wish it was 1,000 tons. 1,000 tons of CO2 per year. And it's outputting around 3,000 tons of materials. And so this plant is designed to treat natural magnesium silicates and slag products, so basic oxygen furnace slag, to produce a bunch of materials. And I'll go over them a bit more towards the end of the project. This is towards the final stage. This is taking carbon dioxide produced from Orica's ammonium nitrate factory on Kooringang Island. So that's where the steelworks also used to be back in the day. And we take that CO2, it's actually in for this process pure CO2 because it's just intrinsic to the process of making ammonium nitrate. But then we process that, we dilute it to validate our technology that can directly capture from flue. And then we're producing materials from that for test programs associated with our industrial partners. The first people that have first customers that are lined up for this is RHIM, but we've got another few potential customers in the pipeline. Moving forward into that industrial scale, the roadmap that we have is currently 1,000. We're looking at in the next couple of years scaling up to about 50, then forward on to 250, and that's going to be based in Austria. So part of RHIM's in terms of their circularity. So they're a company that produces refractory, and they do that by calcining magnesium oxide. Sounds a little bit ironic in terms of using the magnesium carbonate that you produce to recalcine. So what they're looking at is doing circularity, so having a closed CO2 loop in their refractory production. And so that's a system where they mine a magnesium silicate and they produce a magnesium oxide through it without any geogenic CO2 release. So I'm going to give an example today, and I think it's quite interesting. So we originally got into steel slags through Australasian Steel Association. So Craig Hardrich reached out to us. And from there, we've done a lot of work with ASMS at Port Kembla. But it's also familiar because we have Whyalla just across. I'm not from South Australia, so I don't know if it's just across, but it's over there. And in the case of Port Kembla, or just in general, production of steel via the blast furnace way produces around 126 kilograms of slag per crude steel. Down at Port Kembla, if you've ever been down there, there's legacy stockpiles where they've put this in the past and it sits there. They've now increased the way that they can treat it, and they pretty much are able to utilize a fair chunk of that, but there is still material that's not being utilized. Kooringang Island in Newcastle is made out of blast furnace slag, BOS slag. And so it is a legacy problem that exists in the industry, very much for ash ponds. And I think you did a fantastic job explaining the blast furnace slag, Kane, but we know also at Whyalla that they're looking at putting EAF furnaces in. So it is a BF BOS process at the moment, but they are moving towards blast furnace, EAF, and that's supported by both or state government by the looks of it. And if you move down that pathway, you no longer have blast furnace slag. So that's something that needs to be managed. And you've also got a new slag that's going to be coming on the scene, which is an electric arc furnace slag, which has quite different properties to the industry standard, which is a BOF. They are a challenging material to deal with. If you want to do anything with them, you need to store them in stockpiles for up to 3 months where you let them naturally age. And so that's quite a resource intensive process because you have to spray them with water. You have to allow that free lime that's in those materials to naturally hydrate over time. And they become only after time that you can actually use them safely as an aggregate. But that problem that makes them, that free lime that makes them problematic in uses for construction up front is actually an advantage. And so you can take that high calcium oxide content and you can treat them through mineralization. So that's the core technology that MCi has. And that opens up new pathways for valorizing those materials. So here's some technologies that we've developed at MCi. This is largely going to be based on the BOF products, the material that's produced from at the moment Whyalla and also Port Kembla. Typically, we take the air-cooled BOF slag that's normally handled by a third party. It's crushed, the metals, typically the waste metals removed from that and sent back to the steel mill. And then you end up with a material that's classified according to what the handler would like to do it. We take that material and we'll process according to what the objective is. So what I've got up here is two essentially product families. So one is maximizing CO2 uptake and one is maximizing valorization of the material. In the first one, what we've got is carb slag. And so this material, we typically mill down to cement fineness. Again, it is challenging because it is a slag and you have to select appropriate milling equipment so you don't destroy your mill. But we process this down to around that 45 micron fineness, and then we directly contact that with the CO2 exhaust. And what happens there is that free lime component and also the lime or the calcium that's in that glassy component of the slag is reacted and converted to calcium carbonate. And what you end up with at the end of the product is a material that's around 65% calcium carbonate, cement fineness, but you've stored about 280 kilos of CO2 per ton of slag. In the process of making this material, you've stored a fair amount of CO2. What we've been targeting in terms of this material is looking at it as a potential mineral addition or filler in cement. Kane, you put up the picture. Typical GP cement or just cements in general, Australia around 7.5%. I know Adbri are very pushing GL products, which is fantastic to hear. And so this is a potential material that can be blended with natural limestone resources because there are prescriptive restrictions in terms of the limestone quality that you can use in a cement. And that falls under 3972. So these are one of the materials that we've been looking at and we've been working towards seeing how that material can co-blend with natural limestone sources to help reduce the demand on that material. On the right, we have another family which contains manufactured sand and a manufactured limestone. So very similar to what you're showing, Mitchell, with the ground glass here is that we've developed up our process where we can crush and beneficate our slag materials so that we can grade them to a material of direct value. So here we've developed a conditioned graded sand. And so this material essentially has all that free lime component removed that causes the unsoundness issues when used in concrete. In the process of doing that, we take that lime that's problematic and we're able to separate that through grading. And that allows us to produce a manufactured limestone material. So similar to the carbonated slag, except that the main component of the slag is separated through the production of sand. This material has a much higher calcium carbonate, so typically around that 65 to 75%. So it's touching on the compliance level for AS3972 for direct utilization in cement. And similar to the carbonated slag, we've been exploring that material as a mineral addition. And it's quite an attractive opportunity there because we're taking a slag, which is otherwise a waste material, storing CO2 in that material, producing two valuable products that can go back directly into the construction industry. We've been working with a few people to look at both fine sand replacement in concrete. We grade that. If you're familiar with the Newcastle region or the East Coast, is that there's a very good graded sand called Macca's sand. And so that's typically what we're working with. But being an engineered material, we can easily grade that to what the specifier requires. So similar to what you're looking at for the ground glass as well, we're looking at the bedding applications for that and slowly working with partners in terms of pushing that forward. And that summarizes my speech today, and thanks for listening, everyone.